Well, hello and welcome to Bio 211, AMP1, and this is Chapter 2, and we're in the second preparation, and we're beginning with chemical reactions here. And if you've read this inside your textbook already, you know that all we're really looking to do is create new bonds, and or old bonds will be broken, because remember, all chemical reactions are either the giving or taking or sharing of electrons to form something new or break something apart. And that's what we mean when we're saying this here. And we're looking what the metabolism is inside the body. Remember, inside your body, inside Chapter 1, we saw that we either had anabolic reactions, B-O-L-I-C, or catabolic, B-O-L-I-C. And you're going to notice inside your textbook, they now change the actual vocabulary as they're going along. Anabolic reactions are going to be called specific types of synthesis reactions. So let's put a double one in there. Synthesis reactions, or hydrolysis. Let's put another one in there. Hydro, L-Y-S-I-S. Hydrolysis. Okay? So I guess that would be 3 if we're going to do it properly, right? Okay? So the point here, it took a minute or 30 seconds of my time, is as we're going along, we're using the same ideas. We're changing the vocabulary. It's up to you to make sure you use the vocabulary properly as we're going along. Okay, so why? Why is this happening? Why do we actually have to have chemical reactions? Well, because not only is there a law of conservation of energy, where the total mass of the reactants equals the total mass of the products, where if I was going to say something like this, A plus B, whoops, it's supposed to be plus, Jonathan, plus B is going to give us, let's go like this, is going to give us AB. The mass of these should be roughly the same. Okay, the total mass of the reactants equals the total mass of the products. So this should be a total of conservation of mass. Right? Number 1. Number 2, the total mass of reactants has a certain amount of energy inside each of these. And that energy, of course, is potential energy. T-I-A-L. Energy. Okay? So that energy shouldn't change at all. It may be lost as the chemical reaction occurs, meaning radiant energy may be lost to the environment. Okay? But now we actually have the law of conservation of mass as well as energy to help us explain how chemicals enter into chemical reactions. And it's the truth. There are these two laws, the law of conservation of mass and the law of conservation of energy, where neither can be created nor destroyed. They're just simply going to take different shapes. Okay? Having told you that, what we need to tell you, of course, is energy is the capacity to do work, and kinetic energy is the energy associated with motion. And potential energy is that energy that is stored due to its position, meaning it's not actually doing anything. It might have some low-level vibrational energy or whatever, but who cares? Your textbook uses big fancy words for this. Exergonic reactions, in which the bond being broken has more energy than the one being formed, so the energy is being released. Okay? Occurs during catabolism of food molecules. If you think about how cold and hungry you were at one point in time, then you ate a sandwich, all of a sudden you got warm. Okay, part of that is because you're breaking bonds and you're utilizing energy to do that. An endergonic reaction is just the opposite and thus requires energy be added. Okay, usually from a molecule called ATP. For those of you who don't know what ATP is, this is adenosine triphosphate. Adenosine triphosphate. Okay. Yep. Okay. And it's an intermediate of energy. We break a bond, we release the energy from it, okay? And we utilize this. So we utilize ATP to release energy so that we can actually store energy inside of their bonds. And the reason why we do this is because chemical reactions have an energy of activation or activation energy state. Here are the energy of the reactants here. Here is our A plus B, A plus B. Okay, and the energy of activation is holding them in alignment, exciting the electrons such that when we make the product, all of the electrons are now having their octet rule favorably enforced or enabled. Okay? And this energy of activation is the energy absorbed to start a reaction. This is the investment up front. And energy released as new bonds are actually being formed. That's what you're seeing here. Okay? Sorry about this. Let's see if I can get this out of the way. Okay, fantastic. Now, what's going on is Mother Nature can facilitate this, right? Because all what you're actually looking at here is a series of collisions. And to change the amount of energy of activation, Mother Nature can create a catalyst. And catalysts are those inorganic reducers of the energy of activation, whereas enzymes are the organic reducers of the energy of activation. Okay, so how do we actually change this? What changes inside of a chemical reaction? Because here we have the arrow going this way, right? Okay, because remember there are 4 different types of arrows or reactions we want to be thinking about. What are the factors that actually change chemical reactions? Well, concentration of both the reactants. So I was going to say both reactants. You could have more than 2. Temperature increases the likelihood that collisions will occur. Catalysts are chemical compounds that speed up the reaction by lowering that energy of activation. Okay? And it doesn't actually alter the difference in the potential energy. So at the end of this, the catalyst has done its bit. The reaction has gone and done its own thing. Nobody is utilized. I mean, the way your textbook says it is the catalyst itself is unchanged at the end of the reaction. Okay? And that's completely true because all it's doing is facilitating the reaction. Okay? Cool. So what does this look like? So I just drew it for you. The blue line, of course, is with the catalyst. The red line is without the catalyst. Put your A here and your B here, and this gives us our AB, and it shows the amount of energy needed to actually go to product is much less, and that's what's supposed to happen. Now, there are 4 types of chemical reactions. We've been through this. Synthesis reactions are anabolism. Decomposition reactions are catabolism. Exchange reactions are where we are going to switch around the different elements, just like we would exchange them. And then reversible reactions are in different situations, a product can be converted back to its reactants, and then the reactants can be converted back to its products. Okay? And a moment ago, I said, look, anabolism is what we saw back in Chapter 1. Now in Chapter 2, we're calling it synthesis reactions, and I'm even going to go so far as to do this for you. We're going to go start calling it by the other name your textbook will call it, D-R-A-T-I-O-N, synthesis. Okay. Whoops. Dehydration synthesis reactions. Okay. Decomposition reactions are still going to be called those hydrolysis reactions, I said a moment ago. Hydrolysis reactions, which is also catabolism. So what I'm teaching you here and what I'm hoping you're paying attention to is that in the span of 20 some odd pages, you now have 3 different names for the same type of reaction. And again, you need to know all of them. So what's going on? Well, let's take a look at inorganic compounds. Usually they lack carbon and they're simple molecules, whereas organic compounds always contain carbon and hydrogen, and they usually contain this in the shape of a covalent bond. So if we remember what covalent bonds mean, it means that they're strong bonds, and they're really strong bonds that are going to help us build materials. If we think about what now water is doing, water is the most important and abundant inorganic compound in all living substances because of its polarity. Remember, it is a polar covalent bond. And what it does here in this cartoon, here's that salt I was telling you about earlier. Sodium here in green, chloride in yellow. And what happens, of course, is the water begins to surround each of these molecules. And what it's doing is it's temporarily fulfilling the octet rule for sodium. It's temporarily fulfilling the octet rule for chloride here as well. Okay, but it keeps it in solution. Remembering that these are now charged, it means they're carrying potential energy in the unstable configuration of a positively charged sodium ion and a negatively charged chloride ion. Mother Nature can make that work. Okay, so water's a solvent. Yay. There's going to be nobody who's going to disagree with that. Some things are like water and they're hydrophilic. Some things do not like water and they're hydrophobic, but that's what actually makes it useful for us. The other is it can absorb a large amount of heat. It has a heat of vaporization. Okay, and this is what we actually take advantage of. This is what we take advantage of when we're thinking about. So it's now possibly a hot time during the year, or even in the cool time of the year, you can see where water actually leaves the skin. Okay, and as it's leaving the skin, it's actually taking heat with it. Okay. How do we actually start mixing all of this stuff together? Because it's going to be important. If I took the human body apart, you would actually have three basic types of mixtures, okay, where it's a combination of elements or compounds that are physically blended together, but not bounded by chemical bonds. So a solution is a substance called the solvent, water inside the body, okay, and anything that's dissolved into it is the solute. Now, a colloid differs from a solution mainly because of the size of the particles, okay? The colloid has enough, or the particles are large enough that they can scatter light, okay? Now, suspension is main materials, okay? They're suspended, but they will essentially settle out over time. And if you think about things like blood in your body, if I took a volume of blood out of your body and I didn't do anything to it and just let it sit there, it would separate by mass. Okay? So depending on the force that's acting on it, it will determine what's actually going to happen. Now, everything has to be at a specific concentration inside of your body, right? And that's the way that we actually measure the differences inside of our body. And we only know this because, of course, we go looking for these things. The concentration of a molecule is a way of stating the amount of that molecule dissolved in that solution. And anytime you provide a drug to a patient, you need to figure out, well, what am I dissolving it into? And that will give me the amount I should be putting in. And so if you're given, you need to put a 0.005% solution of a specific drug, you need to know what the volume of that solution is given the percent of the drug you have to give them. Now, a mole tends to freak people out, creep them out, whatever. And this is, of course, just a description. And you'll notice I'm not using Avogadro or anything like that. Is the name of the number of atoms in an atomic weight of an element, or the number of molecules in molecular weight of that specific molecule. So we're not counting atoms here. And if we wanted to make you make molar solutions, which you should have done inside chemistry, we could have you figure out the molar concentration of everything inside of your body. But it's already been done, so why have you reinvent the wheel? Instead, what we want you to do is to understand how we use it. And that is, imagine, if you will, we have something like pH. And pH, of course, is the logarithmic scale is the molar concentration of either hydrogen protons or hydroxide ions, okay? Which means you have 10-fold more hydrogen protons, okay, than that of the previous concentration. And that's what we mean by logarithmic molar concentrations. Inside your textbook, you're going to see this pH scale. There is some value to it. What I'd like you to see, of course, is it's a description in a rectangular format. It has an angular line that passes through it, and there are tens located throughout the cartoon itself. In the upper blue part, you'll see it's a light blue to dark blue gradient. The light blue suggests that there are 0, essentially 10 to the minus 14th molecules of hydroxide ions. Okay? And in the lower part, you can see in red, 10 to the 0, deep red in color, the number of hydrogen protons. And this is moles per liter. Well, what that means is, of course, at 10 to the 0, it's unity, which means it's the highest concentration possible for that solution. And you'll see the pH is 0. You don't want to be pouring a pH 0 solution on your body. It will burn right through you. Okay? However, your body can make solutions that are pH 2 for short periods of time. Okay? And strong pH molecules, meaning high concentrations of hydrogen protons, can break apart both ionic and covalent bonds. So Mother Nature might need to actually do this every once in a while. Okay? So take a look at this. Make sure you understand it. You know, if we look at what neutral means, it has the same molar concentration of hydroxide ions as you do hydrogen protons. But that means if you have a pH 14, 10 to the minus 14th here, essentially it's an alkaline solution with no hydrogen protons in it and essentially all hydroxide ions. Okay. One more thing before we finish this off. Okay? Meaning this production, this piece of it. Okay? How do we actually maintain pH ranges? Because they are ranges. If you paid attention in class or if you have some base knowledge, you know that, whoops, let's go like this. Erase you first. Let's go again. You'll know that there's some wave-like function inside of your body, and what I mean by that is if we're looking at the pH, this is going to be 7.45 here, and 7.35 here. Okay. And what Mother Nature needs to do is she needs to modulate it between these 2 points. Because like I said a moment ago, in some instances you might need to get the pH well below this. In some instances inside your stomach it gets as low as 2. Okay? And other instances we need to regulate the amount of carbon dioxide available or not available. And we need to have a pH closer to 7.45. Okay? So depending on what's actually happening inside of your body. And to do this, what we have are buffer systems. Okay? That's the purpose of a buffer system, is to allow us to modulate what's actually going on. And it does this by converting strong acids or bases into weak acids or bases. And that's the purpose of all buffering systems. Okay? The major buffering system you're going to be paying attention to in this class is bicarbonate buffering system. And it comes in many different forms. But the one we speak mostly about is carbonic acid. Okay.